Now we can prove result 3. If A is a proper ideal, then A inverse properly contains O. Since A is contained in P for some maximal ideal P, then P inverse is contained in A inverse. So it is sufficient to show that P inverse not equal to O. We know that O is contained in this P inverse. Yeah. So once we prove this P inverse is not equal to O, then we can get O is contained in P inverse properly, which is contained in A inverse. So this would imply that O is properly contained in A inverse. So we will prove this result: P inverse not equal to O for every maximal ideal. So we start with a maximal ideal P, and we'll find an element which is not an integer, algebraic integer, that is a non-integer, that means non-algebraic integer, that is always in P inverse. For any prime, any maximal ideal, there should exist a non-integer in P inverse. That is what you have to prove. So we start with any A. We start with the A belongs to P. A is a non-zero entry, a non-zero element of this P. Now choose. We already proved that if we consider the ideal A, then we can get P1 etc. PR, a number of prime ideal whose product is contained in A. We choose this R as the minimum. Okay, we collect all these ideals with this property. Then sometimes we can get P1, P2 is contained in A, and we have some in some case we have Q1, Q2, Q3 is also contained in A. Then these are all prime ideals, obviously. So if this is the case, we choose the least product. Okay, so that this 2 is least here. Here we have 3 product of 3 prime ideals is contained in A. Here we have 2 prime product of 2 prime ideals is contained in A. So if we collect all these products, then we choose this R as the minimum. Okay, if this is the case, then 2 is the minimum. Okay, then this R is the minimum in such a way that P1, P2 etc. PR is contained in A. Okay, that means whenever we have a product of q1, q2 etc. q r minus 1, we can say that this product never be contained in this A. That is the idea of the minimum value, minimum the choice of the minimum value of this R. And we know that any ideal is contained in a maximal ideal. So this is contained in maximal ideal P. So we can say that P1, P2 etc. PR is contained in this maximal ideal P. So this P1, P2, PR are all prime ideals. Then we know that every maximal ideal coincides with prime ideal for this O. We can say that this one of these prime ideals, that is P1, P2, PR, these are prime ideal, and this is a maximal ideal. A maximal ideal means it's always a prime ideal as well. Prime ideal, every maximal ideal is a prime ideal. Then we have P1, P2, product of some ideals is contained in a prime ideal. Then we can say that one of them is contained in P. So without loss of generality, we can choose P1. P1 is contained in P, and these two are maximal ideal right now. So we can say that P1 is same as P. Since the prime ideals in O are maximal ideals, we know that they are coincides. So we can say that P2 etc. PR is not contained in A. This is because we have this R is the minimum value. Here we have R minus 1 ideals. So product of this R minus ideal is not contained in this A. Okay. Now we can find an element B belongs to this product, which is not in A, and BP is contained in A. Okay, because this B is an element of P1, P2 etc. PR, and here we have P, and P is same as P1. So this product is contained in A. Okay, that is the choice of these prime ideals. So we can say that BP is always B into P is always, P is an ideal, P is always B into P is always a subset of A. So we have B A inverse P is contained in O. This is because we know that A inverse is contained in O. Okay, we know that B P is contained in this A, and this A inverse is an element of A inverse. So we can say that this B A inverse P is contained in A inverse, which is contained in O. So we can get this B A inverse P is always contained in O, and B A inverse belongs to P inverse. This is the definition of P inverse. If we consider this as X, we can say that X into P is contained in O. Then this will be an element of P inverse. Now we can get B A inverse is an element of P inverse. But on the other way, we have B is not an element of O. Okay, because B is and this AO is equal to A itself. Okay, because A is an ideal. Then B, we have chosen this B from this P2, P3, etc. PR minus this A. So we can say that this B is not an element of A. This is not an ideal A. This is, in fact, this is, I'll write this as AO as nothing but A. Okay, so B, we can say that B does not belong to this AO. This is the multiple of A with the elements of O. So B is the an element. B is an element of the complement of this. Okay, and intersection with this P to PR. So we can say that B is not an element of this member. That means B is not an element of this. So we have B A inverse is not an element of O. Okay, whenever B A inverse, this is an element A. A inverse is an element of O. What happened here? This B A inverse A will be an element of OA. Okay, this is nothing but ideal generated by A. So that would imply B is an element of A. So we know that B is not an element of A. We can get this B A inverse never be an element of this O. Okay, so we can get an element B A inverse which is not in O, but B A inverse is element of P inverse. Okay, so that is the result here. B A inverse is an element of P inverse, and B A inverse is not an element of O. So this shows that this P inverse, the ideal P inverse, properly contains this O. Okay, which is contained in A inverse. So we can say that for any proper ideal A, we have A inverse properly contains this O. Now we can prove fourth result. If A is a non-zero ideal and AS is contained in A for any subset S, okay, a subset of K with this property, then we can say that this S is every element of this S is an algebraic integer. That is the result here. So we have to prove that for any S satisfying this, that is a subset of O. Okay, for that we will show that A theta contained in A for theta belongs to S. Then we will prove that this theta is an element of O. Okay, because O is Noetherian, we can find a generator in a finite number of generator elements. So A can be written as A is an ideal that is generated by a finite number of elements, say A1, A2, etc. An, where not all these AIs are 0. Now, because A is a non-zero ideal. Then if we consider this result, A theta is contained in A, we can say that A theta is a member of A. Then that can be expressed as a in combination of this A1, A2, etc. An. So Am. Then A1 theta can be written as this A1 is an element of A. So A1 theta is an element of this. So A1 theta is an element of A theta. And we have assumed that this is in A. Then we can say that A1 theta is a member of A. Then that can be expressed as a combination of A1, A2, etc. Am. Similarly, this Am theta is also can be written as this form. Now we consider the equation A1 into theta minus, or the other way we can write it as a1 uh, b11 minus theta into a1 plus etc plus b1m am equal to 0 by taking this quantity in the transposing this a1 theta in the right. Then etc we have bm1 a1 plus etc bmm theta minus into am equal to 0. Okay, if we have this system of equation, we can say that this system of equation has solution as a1 a2 etc am. That means this homogeneous system of equations has at least one non-zero solution. Okay, this would imply that the determinant of coefficient matrix of this system is 0. Okay, now we can say that the determinant b11 minus theta, b12 etc b1m, this is the coefficient matrix here, and bm1 etc bmm minus theta, this determinant is 0. Okay, when we expand this we can get a monic polynomial in uh, theta, and whose coefficients are elements of coefficients are bij, these are elements of O. So from this you can say that theta satisfies a monic polynomial whose coefficients from O. Okay, then we can say that beta, this theta is an element of O. Okay, this proves result 4. Now we can prove 5. If P is a maximal ideal, then P inverse equal to O. That means our result P in A inverse equal to O will prove this result for every maximal ideal first. So we start with the maximal ideal P, then P inverse is an ideal, and from 2 we can say that this P is contained in P inverse, that is contained in O. Since P is maximal, this if P inverse is always a fractional ideal which is contained in O, we can say that this P inverse is an ideal. So P inverse is an ideal which contains this P. Okay, but our assumption is P is maximal. So we can say that P inverse equal to P or P inverse equal to O. Whenever this P inverse is equal to P, this is not O, this is P. Whenever this P inverse is equal to P, what happened? We can say that this P inverse is contained in O. That is what you have proved in the result 4. Whenever we have A, S is contained in A, we can say that S is contained in O. So whenever P inverse is equal to P, this P inverse is contained in O. Okay, this is a contradiction because we have proved that P inverse properly contains this O. Okay, so this would be a contradiction. So we can never assume this P inverse equal to P. That means P inverse is equal to O. So this proves result 5. Using 5 we can easily prove 6. So we start with a non-zero ideal A instead of maximal ideal. A inverse, will prove that A inverse is equal to O. If not, if we choose a maximal subject to A inverse not equal to A. That means once we consider if this is not true, then you can construct S such that S contains all the ideals of O with A inverse not equal to O. If there exists at least one, then we can say that this is a non-empty collection. Then we can choose the maximal element of that. Okay, so that is what we have considered A here. So A inverse not equal to A. Then A is contained in P, where P is a maximal ideal, because every ideal is contained in a maximal ideal. Then from 2 we can say that O is contained in P inverse, that is contained in A inverse. A is contained in, by multiplying this with A, we can say that AO is A itself, AP inverse is AP inverse here, A inverse, that is contained in O. In particular, AP inverse, when you consider these two inclusions, AP inverse is contained in O. This AP inverse is always a fractional ideal which is contained in O, implies AP inverse is an ideal. But we can never assume A is equal to AP inverse. Whenever this happens, we can say that this P inverse is contained in O. Okay, using 4, A S is contained in A implies S is contained in O. So whenever this holds, we can say that P inverse is contained in O. This is a contradiction again. So we can say that A is contained in AP inverse. This inclusion is always proper. Okay, a contained in AP inverse properly, and maximality condition on A implies that the ideal's AP inverse is not an element of this set because A is the maximal element of this set. So we can never assume this result for AP inverse. That means AP inverse whole inverse should be O. Okay, this shows that this part A into this equal to O. Okay, so we can say that this is every element of this product is in A inverse. This is the definition of A inverse. Okay, A inverse is defined as set of all x belongs to K such that x A is contained in O. Okay, so we can say that if we consider any element of this, then that element x into A is always contained in O. We can say that that element is an element of A inverse. Then this implies this O can be written as this part AP inverse whole inverse, but this part P inverse AP inverse whole inverse that is contained in A inverse. So A into this can be contained in A inverse. So O can be written as O is equal to this that is contained in A inverse that is contained in O. This shows that A inverse is equal to O. Okay. So for any ideal A inverse is equal to O. Okay. This proves result 6. Now we prove this result is true for every fractional ideal as well. So that is 7. Every fractional ideal A has an inverse A inverse such that A inverse equal to O. For that we assume O is the F is the family of fractional ideals. We know that this is a commutative ring. Obviously it has a identity element O. Then we can choose an if we choose an fraction as a fractional ideal A, we need to show that there exists a inverse another fractional ideal A prime such that A prime is equal to O. Okay, but for every fractional ideal A that can be expressed as C inverse B for some C belongs to O. Now we define A prime as C into B inverse. Okay, so this B inverse is defined for every ideal. We can get inverse of that ideal, and every C inverse there exists C. So this A prime is equal to C B inverse. Then A inverse. What is A prime? What is A prime? A prime is equal to C inverse B and C B inverse. Okay. So now we can write it as B inverse that is equal to O. Now for every fractional ideal we can define A inverse as A prime in this manner. So this proves result 7. Now we can prove every 8th result, every non-zero ideal A is a product of prime ideals. If not, let A be the maximal subject to the condition of not being a product of prime ideals. Okay, that means if we define if there exists at least one ideal which cannot be written as a product of prime ideals, then collect all such ideals. A is an ideal of O. This A is not a product of prime ideals. Not a product of prime ideals. Then this collection, if this collection is non-empty, then it is a maximal element. Let A be the maximal element of that S. Then A is not a prime. If A is a prime ideal, then A equal to A can be written as A is equal to P. That P is a prime ideal. Then we can assume A is not a prime ideal. Then we have A is contained in P for some maximal ideal. Okay, every maximal ideal is ideal of O is prime ideal. Then this maximal ideal is always a prime ideal as well. So we have using the result, A is properly contained in AP inverse, which is contained in O. Okay, now we have AP inverse equal to P2, P3, etc. PR, because this A is contained in P and A is the maximal element of this. Okay, so once you get this AP inverse, we can say that AP inverse is a fractional ideal, and this is contained in O if and only if this AP inverse is an ideal. So this AP inverse is an ideal which is larger than this A, properly larger than this A. So we can say that AP inverse never be an element of S because A is the maximal element. So this AP inverse can be written as a product of prime ideals because every element of S is we have for every element of S we cannot write that element as a product of prime ideals. If an ideal is not an element of S, we can say that that is a product of a number of prime ideals. Say AP inverse can be written as P2, P3, etc. PR. Then clearly A is equal to, by multiplying P on the both sides, we can get AP inverse P, that is O, that is AO, that is equal to A itself. Right side we have P, P2, etc. PR. If we let P is equal to P1, then A can be written as P1, P2, etc. PR. So every non-zero ideal can be written as a product of prime ideals. Now we can prove result 9. In this result, we will prove the uniqueness of the prime factorization. Then first we have a notation. A divides B. These are ideals. When we write A divides B, that means B, there exists an ideal C such that B is equal to AC. Okay, and B is equal to AC is equivalent to A contains B. Because this is the definition of the product of ideals. A product of A and C should contain AC. Okay, sorry, product of A and C is contained in A as well as C. So this is the definition or equivalency will follows from this definition. If we take C is equal to inverse B, then if we write this, suppose we have two types of factorization, P1, P2, etc. PR is equal to Q1, etc. QS for a particular ideal, non-zero ideal, then we can easily get this P1 as a prime ideal, then P1 divides this, then P1 divides this, Q1, etc. QS. Then we can say that P1 divides one of them. Okay, then we can get P1 is equal to some QI. First we can get the inclusion, then because every prime ideal is maximal ideal, we can get this equality for some QI. Then we can cancel this P1 with one of these QIs. So say this is QI, then we can cancel this. Okay, now we can use the induction. First you assume that if R is equal to 1, then P1 is equal to Q1, and if this is not the case, we can say that this if we use the induction hypothesis, the result is true for every number which is less than R. Then by cancelling this, we can get this is a product of prime ideals which is less than, which contains a number of prime ideals which is less than R. Then by using the induction hypothesis that we have used in the prime factorization theorem, we can get the 1-1 correspondence between the ideals of these two expressions. So this shows that prime factorization of ideals as the prime factorization of the elements is unique. So this proves theorem 5.6. So in between we already proved the result 5.5. In 5.5 it says that set of all fractional ideals form a group. Okay, so the only thing what we have to prove is every fractional ideal possesses inverse elements. Okay, that we have proved in the previous results.